before we even start talking about sectors and segments, let's just talk about how we can break up a circle into pieces. So if I ask you what percent of the circle is shaded for this one, what would you say? 50%, right? And how did you get that? How'd you get half? Yeah, 180 divided by 360. Good. Right? Because the whole thing around would be 360, so 180 would be over the top of the fraction. How about 90? 25%. And how'd you find that? Yeah, 90 over 360, which is 1/4. Okay, how about 60 degrees? What percent is that? $16.7. I'm sorry? Okay, did you get it? Okay. And 75 degrees is what percent? 20.8, right? Okay, so we're going to use that percentage thing to calculate the area of a sector. And a sector is like basically a piece of the circle, or like a piece of pie. Okay? I always think of airplanes or submarine movies where they say, Captain, they're in Sector 7, right? Well, it's like a radar machine, and it's going around, and they divide it up into portions, right? So it's a sector. It's a piece of a circle, okay, that is bordered by a central angle and the arc the intercepted arc. All right, so if you think about it, since we don't know, like there's no formula for sector, like just like there is for a square or a rectangle or parallelogram, there's no formula for the area of a sector, but what we can do is we can say, okay, that sector is a percent of the whole circle, and we know how to find the area of a circle. What is that? Pi r squared, right? Remember, pi r squared, pi around. Pi r squared. So if I find the area of the whole circle and then multiply it by just the percent that's covered here, that'll give me the area of this piece. Does that make sense? Yes? So it's going to be pi r squared, the area of the circle, and then the percent. So what would m be then? What would m stand for? Yeah, it would be the degrees inside this angle, right? That's what we did up here. We did 90 over 360, 180 over 360, 60 over 360, right? It's the measure of that angle over 360. So let's try one. So we're trying to find the area of sector DEF. So first I need to find the area of the circle. So what would that be? Right, pi times 16 squared. Now, if I wanted, because r is 16, if I wanted the exact answer, I would just square 16 and leave the pi. So the exact answer is 356 pi. That's the exact area of the circle, no rounding. Okay? But I don't want the whole circle, I only want this piece. So what's the measure of that angle? 36. So I'm going to multiply this by 36 over 360. Okay, but again, if I want the exact answer, I'm only going to multiply the 256 by this and leave pi on the end, right? And 360 is 10%, right? So 10% of 256 is 25.6 pi. So the exact area of this sector is 25.6 pi. And if I wanted the rounded area, I would just multiply 25.6 times, and I'd just hit my pi button, and that comes out to be like 80 point something, 80.4. Okay, so if they ask me for the exact answer, I'd leave it like that. If they ask me for the rounded answer, I'd go ahead and hit the pi button. Pretty easy? Yes. I tend to wait because it takes a little bit of the rounding error off. But if you're just multiplying all three of them together and you're not doing anything else with it, you can just multiply them all three at once. Just make sure that you put the fraction in parentheses. So if you don't put the fraction in parentheses, you're going to get a really small number because it's going to take all of that and put it on the top of your fraction and put 360 on the bottom. So if your number seems really small, like doesn't seem to make sense, chances are you forgot to put the parentheses around your fraction. So go back and check. Okay, so that's a sector. A segment is the piece of a sector, like here would be the sector. If you drew a chord from end to end of the sector, the area above that chord would be the segment. Okay, and what shape do we got here? A triangle. So the way we're going to find the area, because right now finding that would be really hard. So the way we're going to do it is we're going to find the area of the whole sector, the whole thing, and we're going to subtract out the triangle. So if I found this whole sector and took out this piece, wouldn't that just leave that piece, right? So that's what we're going to do here. We're going to subtract out that yellow section, and all that'll be left is the green. So the area of the segment is equal to the area of the sector minus the area of the triangle. So let's try one. Okay, so the first part is easy, finding the area of the sector. That's just the area of the circle times the percent that's covered. So in this case, the area of the circle would be pi times 12 squared. So 12 squared is 144. So that'd be 144 pi. Okay? Then we're going to subtract the area of the triangle. Now, this is when it gets a little, geometry-ish, because I can't tell you exactly what to do next, because it kind of depends on the type of triangle you're given. If you're given a right triangle, you can do 1/2 base times height, and they're both given to you. If you have a equilateral triangle, you can use Pythagorean theorem. If you have some other kind of triangle, you might have to use SOHCAHTOA. So you're going to have to stop and think, what am I given? What can I use? What do I have enough information for? Right? So I can't tell you for sure how to do it every time. So let's look at this one. One thing I do know is, what kind of triangle will this piece always be? Well, it'll always be isosceles, right? Because these are both radiuses, or radii, so they always are going to be equal. So for sure, it's always going to be isosceles. I don't know what else it will be, but it will always be isosceles. So that means the base angles are always going to be the same. If, in this case, what kind of triangle is it? It's not only isosceles, it's equilateral. Good. So I know that this side is also 12, and I know this side's also 12. So the formula for my triangle is 1/2 times base times height. So my base is 12, right? But I don't have my height yet. My height's this one. Okay, but didn't I just draw a radius perpendicular to a chord? So what do I know about the 2/2 of this? They're equal. So if the whole thing was 12, this is 6, and this is 6. Are we okay? So far, so good? Okay. And now I'm looking for the height, but don't I have 2 out of the 3 pieces? So I could go ahead and use Pythagorean theorem. So 6 squared plus x squared equals 12 squared. Because I know the radii are 12. I know this is 6 because it's half of 12, and I'm looking for this piece. So I do 36 plus x squared equals 144. So x squared is 108, and x is 10.3 something, 39. Okay, so I plug that in. Or if it asks for an exact answer, you could do the square root. You could simplify. 108 is divisible by 9. So that's 12 times 9, which is 4 times 3, which is 2 times 2. So the 3's have a pair and the 2's have a pair. So 6 can come out and 3 has to stay in. So if they ask for exact answer instead of 10.39, you would do 6 radical 3. Okay, so 1/2 times 12 times 10.9, 1/2 of 12 is 6. 6 times 10.39 is going to be something around 62, 63, 62.34. That's the formula for the area of a rectangle, right, or of a triangle. So 1/2 base times height. So, but if I wanted the exact answer, instead of doing 1/2 times 12 times 10.39, I do 1/2 times 12 times 6 square root of 3. Because these two are the same thing, just written different ways. So that'd be, if I wanted to have an exact answer, 6 times 6 is 36. So the triangle would be 36 square root of 3. Okay? But then, so if I wanted an exact answer, I would just have to leave it like this. That's not pretty, but it's exact. If I wanted an inexact or rounded answer, then I would type in my calculator 144 times pi, and then minus 62.34. So that'd be like 400. What do you get? Anybody type it in to get the rounded version? Say again. Okay. Yeah, exactly. Okay? Does that make sense? So far, so good? Yes. Last but not least, we want to find the area or the length of a arc. Okay, not in degrees, because if I said, I don't know, Joy, would you run to the store for me? It's only 17 degrees away. Would you have any idea how far that is? No. Like, is it 17 degrees of a 17-mile wide circle, or is it 17 degrees of a 3-inch circle? Like, you don't know. So to find out the actual distance of that, we're going to use kind of the same theory. We've got to find the area of a sector. Remember, we took the area of the whole circle and we multiplied by the percent. So to find the area of a piece of the arc, you know, the distance you would have to walk from F to G, that's a percent of what measurement? What do you call it when you go all the way around a circle? Circumference. So we're going to take the percent of the circumference. Okay? So it's going to work the same way as the area one did, only instead of pi r squared, we're going to use 2 pi r. All right, so to find the length of FG, to find the distance we'd have to walk from F to G, okay, or an ant would have to walk. This is only 8 centimeters, so it's pretty small. You do 2 pi r times, and then the percent that you're covering. So 134 out of 360. Okay, and make sure you put that in parentheses. And again, if they ask you for the exact answer, you have to take 2 times 8, which is 16 pi, and then take the 16 and multiply it by the 134 over 360, being really careful to make sure it's in parentheses, because if it's not, your answer is going to be wrong. It's going to do order of operations, and it's going to multiply before it divides. So the exact answer, what is 16 times 134 divided by 360? 18.71 pi. Oh, so you did? I thought that was right. Are you sure? I thought it was 18 with pi. It's 5.9? When you multiply pi? Okay. Okay. I felt like I remembered that differently. Okay, so 18.7 pi. Let's do the 7. So we did 16 times 134 divided by 360. You just, my brain does not want to believe you. I get it though. 18.7. And then 5.9 pi? 5.955.